A little background. I think it's part of the coder experiences. I found fascinating writing something which directly controls the hardware. No, something like an operating system which has access to full access to the hardware, so we can talk directly with the hard stuff. I think starting is very simple because, for example, we can just write floppy image, which takes control of the machine at the startup, at the boot, and can control the interrupt and write something to the screen, for example, and then hang because there's nothing to do, just to start to do something like that. What's the next step? And that's the result, basically. No, the classic hello world. What's next? That's the dream for coders, no? Creating something more complicated, like the HAL 9000, for example. But what's really next when you, after that you have played a bit with the text? No? The next thing is usually you want to draw some graphic to the screen, and you do it usually using the so-called mode 13, which is one of the oldest graphic modes, which lets you represent pixels with a single byte, meaning we have 256 colors available. And it's pretty simple to handle the graphic in that way. But once you advance with your work, with your own OS, you want to do more, of course. So the basic 886 mode, which is called the real mode, is very limited. It's the old one, and as you can also only code with 16 bits code. You can access only 1 megabyte of memory, and there's no paging and other cool features which nowadays we have. So what you do next is trying to switch to the so-called protected mode. In such mode, we have full access to the memory. We have 4 gigabytes of memory, or with the new 64-bit hardware, you can also access terabytes of memory. You have 32 bits code and also 64 bits code, and you can also have paging and other cool features. Unfortunately, when you switch to the protected mode, you have some problems because many things which usually the BIOS services provides you are not available or doesn't work. So what's the typical solution? When you need some service from the BIOS, you switch back to the real mode, or use the so-called virtual machine, 886 virtual machine. Unfortunately, such solutions have drawbacks. Because when you switch, for example, to real mode, you have to handle yourself the interrupts. So you have two choices. You can route the interrupts to the protected mode, or you disable the interrupts and then enable when you are back on the protected mode. But also, when you execute some real mode code, sometimes it tries to go back itself to protected mode, so it can create problems. And also, it can try to directly access hardware, for example, changing the clock and so on. Another thing, you can use the virtual monitor 886 for that stuff, for controlling that stuff. But unfortunately, this special mode is not available anymore with the 64 bits architectures. So what you can do to solve that problem is to create an 86 emulator. This emulator has a lot of pros because it can work in whatever mode. It also can work on any architecture because you can implement it in also for ARM, for MIPS, PowerPC, and so on. With this emulator, you can also route any hardware access to the controlling OS, and also if the emulator tries to disable or enable interrupt, it can be forwarded to the host OS. So basically, you are running everything inside in a perfect sandbox. Unfortunately, such solution has some drawback also. It's slow because we are emulating something, and also requires a lot of work and testing too. Why I've chosen to write another 86 emulator? For several reasons. Because the existing ones are difficult to adapt to what I need, and then I will talk about that after. For licensing issues, because many times that stuff is in GPL, and GPL is a viral license. You cannot use that stuff in your project, and otherwise you have to release it and so on. Some emulators are weak because they don't implement everything for the 86 or are too perfect, so they means that they are pretty slow. So writing another one means that it's very easy to read, maintain, and modify, and make some experiments with it. We also can have acceptable speed because you can decide to make the common cases fast. And also it's fun, of course. What's the planning? So the real reason for creating such emulator is because it's just the first step of a planning. So the first is creating the emulator itself in Python with a big unit test. Then write a very simple PC emulator, high level, in Python 2, because I want to check real code against it. Then I want to convert such prototype in C for speed reasons, and also for integrating it on a new operating system. In my case, it's an hobby OS, which is called AROS. Why AROS? Because it's a lightweight OS, it's small, it's very easy to understand and study and experiment also, of course. It's an OS which is derived from the Amiga operating system, if someone knows it, and also for just passion and fun. What AROS needs, but working with an hobby OS is something which has a lot of problems. But the main things are the lacking of drivers, basically. If you have a new OS, means that you have no drivers at all, and you won't have to create them, basically. If you have an OS which is different from others, from the APIs and the API point of view, like Amiga, for example, it's not Windows or Unix, POSIX compliant and so on. So basically, add a different set of APIs and API also. So it's very difficult to port the drivers to such OS. The primary need with a new OS is basically having the graphic card working, basically. Otherwise, you are stuck with text, for example, or just some simple graphic mode. When you don't have driver for your graphic card, unfortunately, you have to switch back to the so-called VESA mode. VESA mode provides just the graphic frame buffer, and use it directly, basically. So no hardware acceleration at all. Unfortunately, with the VESA mode, we have also some issues. The most important one is that if you use some solution, some bootloader like Grub, it provides you the ability to set up just one screen mode for your screen. If you want to change the resolution, for example, or depth, unfortunately you have to reboot your OS, your entire OS, and that's something really bad. So what is the solution for such problem? The solution is calling the VESA BIOS with the so-called interrupt 10, which provides a list of useful services. So listing the available modes for graphic card, you can set the mode, change the palette, and so on. So some cool stuff. How the trick works. Basically, once you have the emulator, when AROS boots, it initializes the emulator, and then it's now ready to accept some commands. So, for example, if you need some service for the VESA, the proper graphic driver calls the interrupt 10 with the emulator, passing some parameters. So I need this stuff. And then the emulator execute the 886 code. It also can call some callbacks to signal to the host OS what's needed. If you need to disable interrupt, enable interrupt, or if you need to access to the port IO hardware. And at the end, when the emulator ends its job, the driver gets the results. Okay, now an overview of the emulator. The emulator provides some APIs which are exposed to control the status, and also to set some callbacks to be called by the emulator. And there are a couple of APIs to run to start the execution and to stop it, of course. By design, the execution can hang. What I mean? I mean that if the emulator, for example, stick on a loop, executing forever something, the execution will never stop, of course, because it's a responsibility of the caller, of the host OS, to control the emulator. So, for example, setting up a watchdog and killing the execution of the emulator if it takes too much time. So the emulator just execute code. That's all. It's an emulator. It means it emulates only the processor, 886. It doesn't emulate a full PC. Now a little overview of the 886 architecture. We have just a bunch of 16 bits registers. We have some general purpose registers, 4, which can be also accessed at the byte level, the high byte and the low byte with some special registers. We have some index registers to access memory. We have also the so-called segments. We have 4 segments to control something, to access some special memory. I mean, if I need to execute code with such architecture, I need to use a code segment. So we define a code segment, and then inside the code segment, I can execute instructions from it. If I want to access data, I need to use the usual data segment or the extra segment. And if I need to access to the stack, I need to define the stack segment. I also have a program counter, which is called IP, which combined with the code segment, let me address a specific instruction, of course. And I also have the usual status registers with hold some flags. How I decide to represent the registers, it's just an array, 16 elements of 16 bits, where the first 8 registers basically maps the general purpose registers and the index registers. I also map the segments, the IP, and the flags. I call it, I labeled them internal because they need to a special treatment. We cannot directly manipulate them, usually. I will show it after. So I define the registers in Python. It's very simple. Now I use the xrange function, and I just unpack the values to define the registers and the internal stuff, internal registers. For the segment registers, I cannot write them directly, and I will show you why. And for the IP and flags, I also cannot read them directly. So how I decide to model my registers? I define a class because the final purpose is to create the C version of the such emulator. So with the special class register, I access such registers like I do in C, basically. What I mean is that when I create such instance, It basically defines a pointer to a 32-byte memory area. And I use such area to map the registers. So when I need to read a register, for example, I access such instance with a special getItem method, and I just put, okay, I want AX, for example, and I take the value of the register with a special function which reads a word. A word is a 16 bits value. The same for when I want to write something to the register. I use the special setItem method. The last method I use add because I want to emulate what I do in C. Basically, when sometimes I want to have a pointer to a specific location in memory, which represents the register itself, and I do it with the add operation, basically. So basically, I add an integer, a value, to a register. It means to the registers class. I mean, it means give me the pointer to such register. In fact, that's why I use such class. So I created just one instance of this class. So that's a global value. I decided by design to do it in this way. When I need to access the registers, like I want to have a pointer to the registers, to the value of the register, I just use such function, the first function. When I want to access a byte part of the registers, like AH, AL, and so on, and I use the other function, which basically creates a pointer to the single byte which I need. If I need, for example, to have a pointer to a 16-bit register itself, with the increg function, it shows that, I mean, that stuff. This way I get a pointer to the 16 bits register, like I do in C. And if I want to read the register, I just put the register index in square brackets, like I do in C. If registers is just an array of 16 bits values. For accessing the registers from outside, from the host OS, I also defined some APIs. They are very simple. No, to read the register, just put the index number of the register. To write the register, provide also the value. In Python, I need to mask the value which I write, but in C, using a proper type, I don't need it, and then I put comment for this. And also have the same APIs for reading and writing byte registers. But they are basically the same. Now we take a look at the memory model for the 8086 architecture. Basically, when whatever access I do to the memory, I always need a segment and then an offset. How it works? The segment means that we have a 64 kilobyte area, and then I need an offset inside that area. How the processor works. Basically, it takes the segment, multiplied by 16, which means shift left of 4 bits, and then add the offset. So now we have the physical address inside the 1 megabyte address space. For segments, I also provide some public APIs, which to be called by the host OS. Read segment just reads the value of the segment, while writing the segment is different because I write the value of the segment, but also I need to do some extra operation because, like we have seen in the previous slide, when accessing memory, I need to multiply by 16, shifting, and then adding the offset. So it's an operation which takes time. So I decided to cache basically the segment multiplied by 16 operation using the cache segment private function. So every time that I need to access something on, for example, the code segment, the code segment multiplied by 16 it's already cached in a proper structure, which is an array which is called the segments addresses. Okay, now I need also to model access to the memory using something which is familiar with C. Because I need to emulate also the behavior of pointers which I have in C. How I do it? Basically with the pointer class. The pointer class is made in such a way which it closely resembles the C pointer handling. The constructor basically works in two modes. I can give the constructor, for example, an existing memory area and the position, and it just stores them internally. Or if I don't provide nothing, it just create a byte array instance with the proper size and sets the correct position. So basically, I have a memory area and a position inside that memory area. When I access the pointer instance with the usual square brackets, I just read or write a byte inside that area using the internal position. The C has also some cool stuff which is called the pointer arithmetic. So I need to emulate also that stuff for my emulator. I do it by defining the magic add method, because if I add an integer to an instance pointer, I want to create a new pointer to the new memory location, and the same with the special sub method. Because I can also want to subtract a value from a pointer, so pointing basically to a new memory location. But pointers in C have also another behavior. If we subtract two pointers, basically we get the distance from the 2 pointers. And I want also to emulate this stuff. Everything that is made inside the special sub method. Continuing, in C, usually you can, for example, with the ++, for example, you can advance the pointer of one, or you can also add an integer and so advance the pointer arbitrarily. I do the stuff also with defining the iadd and isub special methods. And the last thing is I want also to convert the pointer to an integer for debugging purposes. For example, I want to display the location of a pointer. So I define the special int method to do that stuff, which basically writes only the current pointer position. I use a few memory data structure for the emulator. One, which is called memory, is a pointer to just a bit of 1 megabyte memory. Then I have also another area which is dedicated to the I/O memory, because the such processor has also a special space address for accessing peripherals, which is called basically I/O. And I also define some the data structure for holding the cached segments. I defined also public APIs for accessing memory. I can fill the memory, can read a byte, write a byte, read a word and write a word. Some trivial stuff. How I have to access the words. I need to create two special functions for that because of the so-called endianness problem. The 86 is a little endian processor, which means when you have to save a word, 16 bits value, you have to first save the low byte of the word and then the high byte of the word in the next location. And that's basically what I do when I read a value or write a value. And I use that functions for that stuff. Okay, now we go a bit inside the emulator. What happens when I reset the emulator? I clear all registers, but CS has to be set to all F, and IP can rest 0. Because the first instruction which is executed by the emulator, the processor, and then on the emulator, stays at the location FFF0. After that, I also have to cache the segments like I stated before. Okay, now a little overview about the instruction format. How an 86 instruction is defined. We always have a single byte, the first byte, which is the opcode, which defines what we have to do with that instruction. We have a second byte which is optional, which is called ModRM, and that's used by some instructions which require 2 arguments, basically a register and a memory location or a register. Such ModRM can require also another 1 or 2 bytes for a displacement to access memory. And there are some instructions which require also 1 or 2 bytes for any immediate data. After that, every instruction can be prefixed by a certain number of so-called prefixes. The prefixes are used to change the behavior of subsequent instruction in some way. There's the lock instruction for locking the memory access in a multiprocessor environment. There are some data segment overrides, which means I don't want to use the usual DS segment for accessing the data memory, but I want to use, for example, the CS, ES, and so on. And there are some instructions which can repeat operations like storing data on memory, on a block of memory, can move memory, and so on, which are called repeat instructions. And they use some special repeat prefix for that stuff. And in the end, there's also a wait prefix for FPU instructions, which are not implemented. So what I do when I need to decode and execute instructions with the emulator. By design, I decided to ignore the lock and wait prefixes because they are not useful. But I need to store some segment or string prefix because, as I said before, they can change the behavior of the instruction to be executed. But after that the instruction is executed, I have to clear such prefixes because I don't want to change the behavior also of the next instruction to be executed. Another thing is that I decide by design to group together some instructions which have similar behavior. I will show you after that. Another thing, there's a special instruction which should be I have to care, because when I write a new value to the SS segment, the processor has to execute the next instruction immediately. So in an atomic way, basically. Okay, now I show you the main loop. The main loop for the emulator is very simple. It resets some value, sets the running variable, and also at the beginning of the execution we have no segment override and no repeat prefixes. And in the main loop, what I do is very, very simple, because I get 1 byte from the instruction stream. I split that byte in a macro opcode and its parameter, and then I execute the function which is bound to that macro opcode, passing the given parameter. The reason is this. If you take a look at the opcode table of that processor, we can see now there is some patterns which repeat. For example, for the add instruction, we have some forms of that instruction. We have a binary head which takes one memory operand, one register, and it's 8-bit. And we have exactly the same stuff for the OR operation and for the ADC operation and so on. We also can take a look on the right side, because for the exchange instructions, there's also a similar pattern. We have to exchange registers, and we only need to know what registers to register to exchange. So that's why I decided to split and group together the instructions. What happens when I have the macro opcode and its parameter? Basically, I call the bound function. For example, if I have to execute add 16 bits, which has a memory operand and a register operand, I execute the function which is at the bottom. And what does the function? It basically gets the ModR byte, which is then, and extracts the address of the memory location and the register to use. Then reads their value and send them and the address to the real function, which is stored in the code variable. It means for an addition, we will call the add 16-bit function. And that's the real function which does the real work. And it's pretty simple for the addition. It's because it basically stores the operands, calculates the addition of the operands, and stores them in the flags result variable. Then writes the result on the address. On the address, and then stores also the operation made on another variable. That's very simple. I talked about the ModR byte, and the ModR byte defines how the two arguments which are needed by the instruction are encoded. So I said before that we have a register and we have also a memory operand. The register is stored on 3 bits, and the mode and RM fields define exactly the nature and of the memory operand, because the mode defines if it's a memory operand or a register, and if it's a memory operand, it's defined what kind of address mode we have to use, and which is stored on the RM field. There's a special case for direct address which is defined by mode 00 and the BP plus displacement mode. So what I do when I have to decode the ModR, I get the byte of the ModR, and then I extract the bits for the ModR, for the RAM field and for the mod field. And then I need to calculate the offset in the memory location. I do it using the special ModR offset array, and then I have to calculate the address for the physical location of the memory. At the end, I just extract the register part of the byte of the ModR byte. Okay, now we take a look at the flags. The processor defines several flags. Some are called system flags, like interrupt, trace, but most of them are application flags, which are used by all instructions, basically. Some of them are reserved, so should be 1 or 0. For the flags, okay, when we execute some operation, the operation can update the flags in some way. There are several scenarios for that stuff. The usual arithmetic operations updates all the 6 user flags. But there are exceptions also. Some logical instructions update only some stuff. The rotates, for example, are a very special case which updates only the overflow and carry flag, and keep all the other the same. Fortunately, some instructions just don't define the content for some flags. The problem with flags is that calculating the flags has a huge impact on performance. That's why. Basically, imagine that you want to just to add two numbers with such processor. Okay, you make the operation, you have the result, but also you have to update the flags based on such operation. It means that you have to calculate 6 flags for that, and as you can see, it requires a lot of operations. So, since instructions like addition, subtraction, and so on are very common, if we always execute that stuff, the emulator speed will be very, very slow. So I decided to implement something different, what I call the quantum approach to calculating flags. Basically, when I do some operation, I don't calculate the flags. Well, I only store the arguments, the result of the operation, and roughly the kind of operation which I made. That's all. What I do, when I need to read some flag, I collapse that flag, only that flag, and take a look at the value. So if I have a few flags to take a look, I just calculate their value and take a look. That's all. Unfortunately, if I have to read many flags, it doesn't make sense to just pick one of them separately. I just calculate all of them. Unfortunately, the rotates instructions are very complicated to be implemented in such a way, so I decided to calculate always the flags in only this situation. But it's pretty rare, so we can live with it. A rough example. In assembly, usually you find such kind of patterns. When you have a loop, for example, you have to compare if the loop is ended by comparing some register, some memory with 0 or with a value, and then jump accordingly if we meet the condition or not. No? If you take a look at the compare, for example, the compare operation does very, very simple stuff. Just store the operands, calculate the comparison, which is basically a subtraction of the arguments, and then stores the operation made, which is a subtraction. That's all. It's very simple and fast. But when I have to execute the jump instruction, the jump is conditional. So I need to check if the 0 flag is not 0. What I do is basically, based on the specific condition, I decide to read only the flag which I need, which is I need to calculate the flag value. In what way? I take a look at the result of the last operation, which is the compare, and check if the result is 0 or not. And I give back to the jump instruction that value, and only that. So I execute a few instructions to do the comparison and the jump. And it's very fast this way. So how to test that stuff? When I written such emulator, every time that I have written a feature or I've implemented an instruction, I also written at least one test for that stuff. I also decided to test all the public APIs, and I try to cover as much as possible of the scenarios, taking also the time to do it. That's because the tests give me an assurance, a confidence that if I change something on the emulator code, I don't get mad trying to figure out if there's a nasty bug introduced. For doing that stuff, I use the usual unit test module, which is very well supported by the Python tools for Visual Studio, which I use for development. Oh, some tests in action. Yeah, as you can see, there are some tests which do some simple stuff. Most of the tests are very simple because they just execute some proper instruction of the processor and then take a look at the result of the side effects of the instruction. So it's very simple, and there are a lot of them currently, around 300. How I can test the final C version? When I will do the C version of the emulator, basically I will create a DLL. Then I create a Python wrapper for the DLL. So I import the DLL with the usual C types, and I also set the proper callbacks for that DLL. Then I can just run the test suite transparently, like any regular Python application. The callbacks are very simple because basically I need to set when the processor has to disable interrupts to enable interrupts, or when we have to read or write a byte IO port, and so on. So I just say to the emulator, look, when you have to disable the interrupts, call this handler, for example. Okay, what's missing? The emulator is not ready yet because I had no time to complete it. It's very complex and it required a lot of time. What's left is basically the unary operations, so not, negation, shift, and so on. And I have also implemented the string operations. It's not that much stuff. I think that I covered around 90%, even more of the instructions of the processor. So a couple of weeks and I will complete all the other stuff. I haven't implemented the tracing of instructions. That's a special feature of the processor, which I don't need for my project. So it's easy to implement, basic, but I don't need it, and I don't want to implement it. And I also decided to don't implement some special corner cases of the processor because it will take time to implement, and also it will slow down the execution with no gain for such stuff. As I said before, I don't need the perfect emulation. I need only an emulator which execute well real code. And what I miss is some more test coverage for example, for the ModR RAM bytes, which currently just tests some stuff. So I need to put something on that side also. Okay, I finished it. I have to thank my family, and if there is some question.
Are there questions?
Thank you very much for the talk. It was very interesting. I've never written an emulator, and it would be something that at one point should be done, just for fun. Can you suggest me any resources in terms of how do I get started? Is there any sort of books, papers, or something that you could suggest could help?
For sure, you need to take the architecture manual. So in my case, I took a look at the Intel 86 manual, which defines everything for the processor, defines the register set, the opcodes, and there's also some cool opcode tables which shows you effectively how the bytes of the instruction are made and so on. So you take it as a reference, and then there's also some part which defines the behavior of the processor at the beginning, at the reset, no? And it's very important. You have to know how the processor is initialized, and you have also to emulate the stuff.
Hi, thanks for the talk.
I just didn't get exactly the classes on the first slides. The one, the pointer one, and why did you implement it? For what reason?
The reason is that the emulator is written in Python, but the final goal is to write a C version of it. So I haven't used some Python-specific stuff like comprehensions and whatever classes and so on. But I need also to define some way on for accessing memory, the 8086 memory for the emulator. Since in C we have only pointers to address memory, to do some operations and so on, I need to define a pointer class which basically mimics the behavior of pointers in Python also. So the pointer class basically you can use it like you use a pointer in C. If you need to read a byte, for example, from that pointer, what to use in C is p square brackets and then the offset of the array which you are accessing. And I need to do the same way for in Python. I also need, for example, to advance the pointer. In C, what you do is p++, for example. And how can I do it? I do it in Python with p plus equal 1. Redefining the special method IAdd. With IAdd, basically, I say, okay, this pointer, I have a new offset for you. Please add it to your internal pointer position. So I basically move the position where I want. And that's why the pointer class is so huge. It tries to define everything in C, okay, what we can do in Python. Because, for example, in Python there is no asterisk operator. I cannot do asterisk p in Python. So in that case, I try to use another construct. For example, p square 0, and I do basically the same. But okay, the final goal is this: I try to emulate as much as possible of the pointer arithmetic in Python. So then when I have to create the C version, it's fairly simple. Just get exactly the same or just change something, and the code is there.
Any other questions?
Just one small thing. I know we are at the Python conference, so I don't I don't want to. No, I'm just saying what I mean is there's this really great language which is called Rust. I don't know if you ever heard of Rust lang.
I know it.
Yeah. So Rust for these type of things I think could be quite interesting because it has a lot of low-level components, but in the same sense it has very good syntax, just like Python, for example.
But the thing is, the final goal of this project is to integrate that stuff in another project, which is AROS. In AROS, you don't have Rust. You have C, only C.
But the interesting thing is that you can, basically, because what you are writing, what you at the end, what you do is compile. So, you could potentially find some bindings or something. But it's just. I'm just thinking, if I had to implement this, and your concern, for example, for performance or in general, to have sort of a low-level perspective of things. So not, for example, having to override pointer plus or something like this. Rust, for example, provides, let's say, a part of this, which could be interesting, potentially.
Yes, it's interesting, but if you don't have such language, unfortunately, I have to say that C is the so-called lingua franca. You find any C compile for every architecture, platform, whatever you want. So we have to deal with that stuff. Even C++, for example, is not available in all platforms, or for example, is limited as simply limited stuff. So we cannot use it for such project.
Other questions?
No.
Okay. There are no other questions. Just Thank you again.